pollutants are in the wastewater. Before selecting the process or the technology, we need to set our objectives. That means what is the destination after the treatment. If, for example, we are going to throw the water after treatment to the natural environment, so we need to have a very high advanced treatment, so to minimize the contamination of the water resources. After characterization of the wastewater, so we can set the candidate technology, then to conduct some bench and investigation in the lab, and from the results of the bench scale investigation, so we can run some pilot scale, and through the both bench scales and pilot scales investigation, we can prepare preliminary designs. And of course, you need some economic investigations to compare different designs and the costs, of different designs. So talking about the different type of wastewater treatment for industrial wastewater. So we have three, I know that you know that we have three methods to treat the wastewater. So we have the chemical, physical, and biological. So I'm not going to go through these technologies because you have presentations by Professor Fatik on this issue. So anyway, we have for chemical using chemical methods using some chemicals like chemical oxidation or coagulation, flocculation. For the physical methods treating industrial wastewater, we have, for example, filtration using membrane. We have also some of the sedimentation. Biological treatment, they are using microorganisms or also plants as fecal remediations. So to treat wastewater pollutants, we can have some examples here like activated sludge, anaerobic treatments. We have also, we can call also bioaugmentation. So this is the steps that we can find in any wastewater treatment plant. So it is combination of physical and chemical biological processes. We start by preliminary treatment. It's kind of physical. Primary treatment, physical and chemical treatment. Secondary treatment, most of the time, is biological. And sometimes we can combine the conventional treatment with advanced treatment. If we are looking for high quality treatment, for example, the use, if we are going to reuse it, especially in the agriculture or in the industry. As I said before, that one of the technology can be used as physical, let's say, technology. We have membrane separation that have experienced that recently, in the recent years, are being applied in the industry today because they have many because of the demand of higher quality, we need water, especially if we are looking for using, recycling the water, because of also increased regulatory pressure. So we need, now the standard, we need to be under the standard of set by the government. The rising interest in preserving also the nature, and because of the environmental economic sustainability. So the reason why we are looking for this technology, because it's actually a clean technology and is getting more easy in terms of operation. It's also compact and modular, especially if some industry, they don't have space for putting their system to treat their wastewater, so it is compact. The membrane also produces high quality of water, and we have also recovery of some fiber debts, and also it is flexible in terms of design, and also it's easy to incorporate in existing industrial plants. So this is a figure presenting the membrane. We have actually the feed, which contains consisting of particles, and we have membrane. So the feed can pass through the membrane, and we have some particle can pass through the membrane. Some of them are faster than others, and the other side we have the permeate. So it is a feed, so we have the two terms, the feed consisting of a mixture of two or more components, especially separated by means of semi-permeable barrier through which one or more species move faster than the other species. So we can have two-flow configuration. We can have the cross-flow operation and the dead end operation. So we can see here a difference between both. So what is the difference? If you see this figure between the cross-flow operation and dead end. There is no difference? Yeah, that's true. Dead end operation, there is no concentrate. And also, so we have here the permeate, the feed is parallel and concentrate are parallel to the surface of membrane for the first, and the second, the feed is perpendicular to the permeate, to the surface of membrane. Next, please. So here the feed flow is parallel to membrane surface, and we have actually the retained particles are scored, and also we have concentrate stream. Second time, the dead end operation, we have the feed flow is perpendicular to membrane surface, and the retained particles form a cake layer on surface, and we don't have concentrate we use it for conducting laboratory research. For example, if you have many kind of samples of membrane, and you want to choose which is the best, for example, membrane to your wastewater. So it is a kind of, let's say, step to choose the best membrane to be used for the wastewater you are working with. We can classify the membrane according to the origin. So we talk about synthetic and biological. We can also classify membrane according to the materials. Its material is solid or liquid, morphology, organic and organic structure, non-porous and porous. So here, if we are going to classify it according to the physical structure, we can find symmetric. That means it's homogeneous with one kind of materials, and the membrane is uniform in density and pore structure throughout the cross section. Asymmetric, we have it's homogeneous also or heterogeneous, so it can be with one or more materials. The density change given by the membrane material across the cross section. The third kind is composite. It's heterogeneous membrane with different materials, and have a thin, dense layer that serves as the filtration barrier. And we have different materials than the porous structure into which it is cast. So as we can see here, that explains more. So we have the symmetric with the cylindrical pores or and homogeneous, so it's with one kind of material. Asymmetric single material, so we have here pores and pores with the top layer. Asymmetric, so we can see there is dense skin layer between 0.1 to 0.5 micrometer, and porous membrane between 50 and 150 micrometer. This is some figures of electrosmithscopy about the structure of membrane. We can see here different structure, porosity, materials, and so on. Even the kind, we can see later the difference between the shape. We will see its flat sheets and hollow fiber later. Geometry. So we have two kinds of geometry. We call one type is flat sheet membrane. It's like paper, and within flat sheet we talk also about spiral wound and flat and frame. Tubular membrane, we have two kinds. It can be immersed or side stream membrane. So we can find also tubes, capillaries, and hollow fibers. I'll show you some figures here. So spiral wound, here it's kind of two membranes separated by spacing to delay the falling. And we can see this is one module, and usually in the industry or even for waste treatment, domestic waste treatment, we use many modules. So it's like for as a pre-treatment. For example, some industry, for example, for pharmaceutical wastewater treatment, or maybe some wastewater contaminated by pesticides, is not enough to treat it by like microfiltration or ultrafiltration. We have to combine it with the first osmosis. So the microfiltration, ultrafiltration, in somehow can be a step, pre-treatment step for reverse osmosis. We talk also membrane bioreactor, submerged membrane. It is actually membrane inside basin of feed water. So, for example, for the industry where they have, for example, activated sludge process, and they are not able to treat, or they are not able to have a good quality of water, treated water, so they can just add a submerged membrane inside the activated sludge basin. And they operate under section. What are the advantages of the submerged membrane? They operate at lower pressure. That means it is not, that doesn't demand a lot of energy, so it is not costly. And less falling, because we have the problem of falling with membrane, but with the submerged one, there is less falling, so it is good for industrial wastewater treatment. And the cleaning is not difficult, and also the fixing. This is a figure of the submerged membrane. It can be microfiltration or ultrafiltration. We have here the basin, we have the hollow fiber, and we can bubble the water, bubble with air as a scoring of membrane surface. And here there is the filtrate to reverse osmosis. This is to show you how can be the submerged membrane can be a pre-treatment step for reverse osmosis. This is to show you, in fact, a comparison of different configuration with many, let's say, parameters. So we can see here the most cheaper is hollow fiber and spiral wood, but tubular and plate and frame are a little bit high. We have also cleaning is very important to see, because when we talk about cleaning, we need more chemicals to clean the membrane. So it is another cost also to think about. So for the hollow fiber is we have, if we are with the so with the for traditional sphere wood, sorry, for the cleanability is not, this cleanability is how much is clean the water, I'm sorry. So here, for the hollow fiber we have good quality. mean it's possible. The materials, we have two kinds, main kinds of materials. We have polymeric membrane and ceramic membrane. So the most popular is polyvinylidene fluoride, and ceramic one we have zirconia or titanium. We can find membrane property. It's very important when we talk about membrane. We need to have to set the properties at the start of the experiment, especially we need to know the permeability, the force size, the molecular weight cutoff. We need also to know the surface roughness, if it is hydrophobicity, the hydrophobicity and the hydrophilicity of the membrane. It's very important to know that. To study the performance, we need to determine two main parameters. We have the flux and the rejection. The flux is the volume flowing through the membrane, and the rejection is the relation between upstream and downstream concentration. So, just to show you the next how to calculate this is how to calculate the flux. It is just, this is here the flow of the water divided by the membrane, the surface of the membrane. And we can also talk about specific permeate flux when we want to normalize the calculation to the applied gravity forces, the pressures. So the rotation rate, so we can calculate, for example, let's say if we are going to calculate the rotation rate for I can show you the next maybe it's better. Later I can explain what I have an example. So the temperature it has an effect to the membrane. So actually when the temperature will be high, so the viscosity will be decreased or increased. When the temperature is increasing. What is the relation between viscosity and so when we have have also deposition of microbiological, let's say, waste of microorganisms. Also, we have organic deposition. So all these kinds can have an impact of the performance of the membrane. So this is why from time to time we need to clean the membrane with some chemicals, mainly acids or base, according to the material of the membrane. So this is when we talk about ultrafiltration or microfiltration, nanofiltration. All these kind of membranes are called pressure-driven membrane processes because we are using the membrane, the pressure. So it is very important to know for what is the pressure should be used for each membrane. So here, for each, for example, for microfiltration, it can remove bacteria and suspended solid. We use filter filtration for macromolecules and gases. For nanofiltration, you can remove covalent ions and reverse osmosis, so can remove monovalent ions. So we can see it's each membrane can remove certain particles. So for the reverse osmosis membrane, we can characterize them with sodium chloride rejection. So we talk about like 96 or 99 rejection. Microfiltration, for example, we talk about pore size. So we talk about their pore size like 0.1 micrometer. For the ultrafiltration, we talk about molecular weight cutoff. However, for the nanofiltration membranes, we talk about rejection of sodium chloride or magnesium sulfate. So this is to show you the selection, how to select the membrane. If we are going, for example, to remove, let's say, gases or vacuum. So we need to look for ultrafiltration. If we are, for example, we are looking for to remove some bacteria. So we don't need to have like ultrafiltration. We just choose microfiltration because as much as we try to choose very high quality of water, that's meaning we need more pressure, that's meaning more energy and more cost. So for the microfiltration here, can remove, as I said, microbes and turbidity. So if we are looking for removing that, we just choose the microfiltration, ultrafiltration, so we can remove viruses and some natural organic matter. especially natural organic matter. So it is a time to reduce the falling. We need to combine the microfiltration with coagulants. We also can combine ultrafiltration with the powdered activated carbon. So to remove, natural organic matter, and this is done also to reduce the falling. Submerged microfiltration, we have also seen the part of submerged microfiltration. Especially, we use them in industry to reduce, to remove iron and manganese. It's very important also to add aeration. And when we add coagulation, especially to remove the natural organic matter. For the nanofiltration, we use nanofiltration as between, let's say, it is a kind of low pressure reverse osmosis. It is usually designed to remove sodium multivalent ions, and they can be also remove sodium and chloride very well. So we use typically 5 to 14 bar for nanofiltration. Ultrafiltration, especially we can see it here, it's from 0.5 to 5 bar. For microfiltration, we use as porosity 0.5 to 5 micron for nanofiltration. So here, just to show you, this is to summarize a little bit the pressure and the flux of each class of membrane. We have here, we can see the pressure is very high, and as much as we are using pressure, we use more energy. So it is very important to set at the beginning your objectives, if you are going to reuse or just to throw it to the nature. This is just to give you an idea about how much there is consumption of energy. You can see that reverse osmosis consumes a lot of energy by cubic meter. It can be 18 kilowatt per hour per cubic meter. So I want just to present now a case of study of textile industry. So I don't know, in Ukraine you have a problem with the industry or not, if you have this industry. So in Tunisia, or I think we have, there is a huge problem with this industry. So this industry consumes a high quantity of water. So there is a necessity to reuse this kind of wastewater inside the industry. The quality of the wastewater is very toxic and non-biodegradable. It contains a lot of organic substances, and on the other hand, there is limitation to reuse because of these non-biodegradable substances, organic substances. So when we look to the process, because I said that it's very important, we saw the different steps at the beginning, and the first step we have to look to the manufacturing processes. So we use the water in many steps in the industry, textile industry. the finishing also, when we finish the product, we need a lot of water. So that means we are using water from 5 to 40 times the fiber weight. So for 1 kilo of fiber, we use 5 to 40 kilograms of water. So this is the main effluent characteristics from the textile industries. So for each step process, each step in the industry, we have wastewater generated with different quality. So mainly it is high DOD and COD. We have also the problem that the water is with very high pH. We have a big concentration of suspended solids, high pH. The color is the main problem because with activated sludge we cannot treat this kind of wastewater. And also we have oily appearance in the wastewater. So the problem with this kind of wastewater, so we have environmental impact and difficult to treat directly through conventional biological processes. That means with activated sludge, it's difficult to have like a good quality, especially if we are going to reuse this wastewater inside the factory. So this is why we suggested membrane bioreactor to be used as a promoting technology to treat this kind of wastewater. So typical wastewater, the mean, that the dyes are between 10 to 50 milligram per liter, surfactants from 20 to 50 milligram per liter. It's low biodegradable. Biomass interaction it's low biodegradable. It's difficult to have a good biomass to treat this kind of wastewater. And also with the color, we don't have enough light to penetrate. If you are going to throw it to the nature, we will have problem with eutrophication. The next one, we have also problem when a lot of wastewater plants using activated sludge, they have the problem of foam, and also at the final the water treated, the color remains. So it is a problem to throw the water in the nature. So we need another technology, at least to remove the color. So the challenge then, I have also to mention that the temperature is very high. The wastewater after inside the factory, it is wastewater around 90 degrees, and according to the regulation, the wastewater should be around 40 degrees. So we can think about how to recover this energy, this heat, and also we have a consumption of 80% of water, so we can think about reusing this water inside the industry. And also the third problem is COD. And I have also said about the color. So we have actually 4 main problems inside this industry. This is some values of a factory in Italy. It's actually just to give you about the quantity of water color is quite high, with at 450 nanometer, and we have also high concentration of nitrogen. For this factory, they proposed a kind of membrane bioreactor, but here the module is not submerged, is side stream. So we have here, like, this is the activated sludge, and we have just to pump from biological to the module, and the concentrate will be recycled to the biological reactor. And here we have the permeate outlet. This is the pilot plant within this factory. The module consists of 4 elements, and it is organic type, and we cut off 40 kg, and we have the equivalent of 002 to 003 micrometer, and we have the flow rate around 30 cubic meters per hour. And here the pressure before and after the membrane. So now, here the color, the result of using MBR with the other technologies. So it's comparison between 3 actually, and you can see here MBR influence has a value which is not far from the one using the ozone effluent. So the next step, it should be actually to calculate the cost to see if it is feasible to choose membrane or ozone effluent. This is a second example. Here, using for the same textile industry, but using membrane bioreactor, which is submerged. So we used this kind of seaweed. It's very popular, let's say, commercial one. And just here, this is the membrane submerged inside. And actually, we have as a result, using the weed, we have actually different, let's say, good results on BOD, turbidity, total nitrogen. It's according, let's say, the standards. So we can say it is promoting technology. So here to show you that around the world there are many textile factories. They did implement in their factories membrane technology to treat their wastewater. We can see here Germany, France, Spain, Italy, Emirates, Bahrain. So we can see even the dates since 2001. There are many membrane factories who did implement this kind of technology to treat their wastewater. As a conclusion for the case study, so many countries have tightened the environmental regulation for all industry. So the cost of fresh water and for disposal of wastewater will increase. So MBR is a technical solution to meet the stringent effluent requirements, and also enable to reuse the water inside the
Thank you very much. Так, ну тогда на сегодня все. Спасибо большое.